Hi, welcome to Unsupervised Learning in Python. Unsupervised learning encompasses a variety of techniques in machine learning, from clustering to dimension reduction to matrix factorization. In this course, you'll learn the fundamentals of unsupervised learning and implement the essential algorithms using scikit-learn and scipy. You will learn how to cluster, transform, visualize, and extract insights from unlabeled datasets, and end the course by building a recommender system to recommend popular musical artists. This course consists of 4 chapters, which are clustering for dataset exploration, visualization with hierarchical clustering and TSNE, decorrelating your data and dimension reduction, and lastly, discovering interpretable features. In this video, we'll be covering Chapter 1 of Unsupervised Learning with Python. In this chapter, we'll learn how to discover the underlying groups, or clusters, in a dataset. By the end of this chapter, you'll be clustering companies using their stock market prices, and distinguishing different species by clustering their measurements. Let's begin with learning about unsupervised learning in Python. Unsupervised learning is a class of machine learning techniques for discovering patterns in data. For instance, finding the natural clusters of customers based on their purchase histories, or searching for patterns and correlations among these purchases, and using these patterns to express the data in a compressed form. These are examples of unsupervised learning techniques called clustering and dimension reduction and quat. The iris dataset consists of the measurements of many iris plants of 3 different species. There are 4 measurements: petal length, petal width, sepal length and sepal width. These are the features of the dataset. Throughout this course, datasets like this will be written as 2-dimensional NumPy arrays. The columns of the array will correspond to the features. The measurements for individual plants are the samples of the dataset. These correspond to rows of the array. The samples of the iris dataset have 4 measurements, and so correspond to points in a 4-dimensional space. This is the dimension of the dataset. We can't visualize 4 dimensions directly, but using unsupervised learning techniques we can still gain insight. In this chapter, we'll cluster these samples using k-means clustering. K-means finds a specified number of clusters in the samples. It's implemented in the scikit-learn or sklearn library. Let's see k-means in action on some samples from the iris dataset. The iris samples are represented as an array. To start, import k-means from scikit-learn. Then create a k-means model, specifying the number of clusters you want to find. Let's specify 3 clusters, since there are 3 species of iris. Now call the fit method of the model, passing the array of samples. This fits the model to the data, by locating and remembering the regions where the different clusters occur. Then we can use the predict method of the model on these same samples. This returns a cluster label for each sample, indicating to which cluster a sample belongs. Let's assign the result to labels. After getting labels, let's print them out. If someone comes along with some new iris samples, k-means can determine to which clusters they belong without starting over. K-means does this by remembering the mean, or average, of the samples in each cluster. These are called the centroids and quat. New samples are assigned to the cluster whose centroid is closest. Suppose you've got an array of new samples. To assign the new samples to the existing clusters, pass the array of new samples to the predict method of the k-means model. This returns the cluster labels of the new samples. In the next video, you'll learn how to evaluate the quality of your clustering. But for now, let's visualize our clustering of the iris samples using scatter plots. Here is a scatter plot of the sepal length versus petal length of the iris samples. Each point represents an iris sample, and is colored according to the cluster of the sample. To create a scatter plot like this, use pyplot. Firstly, import pyplot. It is conventionally imported as plt. Now get the x and y coordinates of each sample. Sepal length is in the 0th column of the array, while petal length is in the 2nd column. Now call the plt.scatter function, passing the x and y coordinates and specifying c equals labels to color by cluster label. When you are ready to show your plot, call plt.show. Previously, we used k-means to cluster the iris samples into 3 clusters. But how can we evaluate the quality of this clustering? A direct approach is to compare the clusters with the iris species. You'll learn about this first, before considering the problem of how to measure the quality of a clustering in a way that doesn't require our samples to come pre-grouped into species. This measure of quality can then be used to make an informed choice about the number of clusters to look for. Firstly, let's check whether the 3 clusters of iris samples have any correspondence to the iris species. The correspondence is described by this table. There is 1 column for each of the 3 species of iris, setosa, versicolor and virginica, and 1 row for each of the 3 cluster labels, 0, 1 and 2. The table shows the number of samples that have each possible cluster label/species combination. For example, we see that cluster 1 corresponds perfectly with the species Setosa. On the other hand, while cluster 0 contains mainly Virginica samples, there are also some Virginica samples in cluster 2. Tables like these are called cross-tabulations in Quat. To construct one, we are going to use the pandas library. Let's assume the species of each sample is given as a list of strings. Import pandas, and then create a 2-column data frame, where the first column is cluster labels and the second column is the iris species, so that each row gives the cluster label and species of a single sample. Now use the pandas crosstab function to build the cross-tabulation, passing the 2 columns of the data frame. Cross-tabulations like these provide great insights into which sort of samples are in which cluster. But in most datasets, the samples are not labeled by species. How can the quality of a clustering be evaluated in these cases? We need a way to measure the quality of a clustering that uses only the clusters and the samples themselves. A good clustering has tight clusters, meaning that the samples in each cluster are bunched together, not spread out. How spread out the samples within each cluster are, can be measured by the inertia and Quat. Intuitively, inertia measures how far samples are from their centroids. You can find the precise definition in the scikit-learn documentation. We want clusters that are not spread out, so lower values of the inertia are better. The inertia of a k-means model is measured automatically when any of the fit methods are called, and is available afterwards as the inertia attribute. In fact, k-means aims to place the clusters in a way that minimizes the inertia. Here is a plot of the inertia values of clusterings of the iris dataset with different numbers of clusters. Our k-means model with 3 clusters has relatively low inertia, which is great, but notice that the inertia continues to decrease slowly. So what's the best number of clusters to choose? Ultimately, this is a trade-off. A good clustering has tight clusters, meaning low inertia, but it also doesn't have too many clusters. A good rule of thumb is to choose an elbow in the inertia plot, that is, a point where the inertia begins to decrease more slowly. For example, by this criterion, 3 is a good number of clusters for the iris dataset. Let's look now at another dataset. The Piedmont wines dataset. We have 178 samples of red wine from the Piedmont region of Italy. The features measure chemical composition, like alcohol content, and visual properties like color intensity. The samples come from 3 distinct varieties of wine. Let's take the array of samples and use k-means to find 3 clusters. There are 3 varieties of wine, so let's use pandas crosstab to check the cluster label, wine variety correspondence. As you can see, this time things haven't worked out so well. The k-means clusters don't correspond well with the wine varieties. Here you can see a code sample of getting variances of all features in the wine dataset and exporting those variances in a CSV file. The problem is that the features of the wine dataset have very different variances. The variance of a feature measures the spread of its values. For example, the malic acid feature has a higher variance than the OD280 feature, and this can also be seen in their scatter plot. The differences in some of the feature variances is enormous, as seen here, for example, in the scatter plot of the OD280 and proline features. In k-means clustering, the variance of a feature corresponds to its influence on the clustering algorithm. To give every feature a chance, the data needs to be transformed so that features have equal variance. This can be achieved with the standard scaler from scikit-learn. It transforms every feature to have mean 0 and variance 1. The resulting standardized features can be very informative. Using standardized OD280 and proline, for example, the 3 wine varieties are much more distinct. Let's see the standard scaler in action. First, import standard scaler from sklearn.preprocessing. Then create a standard scaler object, and fit it to the samples. The transform method can now be used to standardize any samples, either the same ones, or completely new ones. The APIs of standard scaler and k-means are similar, but there is an important difference. Standard scaler transforms data, and so has a transform method. K-means, in contrast, assigns cluster labels to samples, and this is done using the predict method. Let's return to the problem of clustering the wines. We need to perform 2 steps. Firstly, to standardize the data using standard scaler, and secondly to take the standardized data and cluster it using k-means. This can be conveniently achieved by combining the 2 steps using a scikit-learn pipeline. Data then flows from one step into the next, automatically. The first steps are the same. creating a standard scalar and a k-means object. After that, import the make_pipeline function from sklearn.pipeline. Apply the make_pipeline function to the steps that you want to compose, in this case, the scalar and the k-means objects. Now use the fit method of the pipeline to fit both the scalar and k-means, and use its predict method to obtain the cluster labels. Checking the correspondence between the cluster labels and the wine varieties reveals that this new clustering, incorporating standardization, is fantastic. Its 3 clusters correspond almost exactly to the 3 wine varieties. This is a huge improvement on the clustering without standardization. Standard scalar is an example of a preprocessing step. There are several of these available in scikit-learn, for example max_ab scalar and normalizer. Thanks for watching. In the next video of the playlist, we will learn about 2 unsupervised learning techniques for data visualization, hierarchical clustering and TSNE. Also, if you have any questions you can ask them in the comments section and we'll be pleased to answer those for better level of understanding. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. See you in the next video.